Okay, so here we have a pretty simple op amp. I know to a lot of students who are just learning this circuit may not look simple at all, but I promise you it is simple. If you paid attention to my op amp video, my op amp, the teaching section of it all, then you'll realize that basically this device right here is just a double input, one output device. All right, it has three rules. And once you understand those three rules, the three rules are pretty simple, then all you have to do is basically do node voltage on this device, and out is going to come our output. All right, so let's get started. This will be our first example coming off of the lecture, if you will. So what we want to do is find the output voltage of this op amp. Note the in terminal of the op amp is on the top side and the P terminal of the op amp is on the bottom side. Okay. So remember, you want to basically do KCL at the nodes with the stuff. All right. So if you look at which nodes have the stuff, is basically you have in, P, and the output. Output is connected to the in. In has some stuff. P is connected straight to the ground. This whole bottom terminal we can see as a ground. Okay. So if P is connected to the ground, it has no stuff. N has the stuff. So all I have to do is do a node equation at N. I guess I'll do that in blue. So I'll label this node right here N. Actually, this is what I'll do. I'll label this node right here N. And I'll say from our regular nodal analysis, we always drew the currents. So this would be a current passing into this node, current leaving the node, and then there's this current right here going into it. Okay, well, that's IN. We'll call this I1. And, that was a mistake. We'll call this I1 and we'll call this I2. Okay, so if we do a nodal analysis at N, it'll just say at N, all right, I have I1 coming in, I have I2 leaving, and I have IN leaving. That all equals 0. Okay, well, once you've built this equation, you can now label IN equals 0 because of one of the primary laws of op amps. All right, there is no current going into or out of the op amp in itself. So this line right here and this line right here, they get no current. So basically, this I1 passes unabated from the 5 into the 20. Basically, I1 is I2. But when we write it in no voltage form, it gives us equations that are useful in terms of actually solving it. So to express I1 properly, we basically have to say it's the voltage right here minus the voltage right here. The voltage right here is 10. If you say this is the ground, that means the voltage at this node is 10. So you're going to have you're going to have 10 minus the voltage right here, we can just call Vn, right? The voltage at node N divided by 5. All right, this term right here is I1. And then I2, remember you got to put a minus sign. I2 is going to start at N and then end on V out. So you just say Vn, all right, and it goes to V out, so it's going to end on V out minus V out divided by 20. This equals 0. So just like how we did in no voltage, we constructed an equation and we put that equation in no voltage form. Naturally, in no voltage form, I always like to clean it up, so I'm going to clean this equation up really quickly. Multiply everything by 20, I'm going to get 40 minus 4Vn, all right, minus Vn plus V out. Please do not forget to commute that negative, equals O. Now I have an equation that has V out and Vn in it. Let me just solve for V out really quickly. V out is going to equal 5Vn minus 40. All I need now is my Vn. So I'll put need, okay? And then the question is, well, how do I get Vn? Well, if the first rule about an op amp is there's no current passing into and out of it, the second rule will be the voltage at N is the voltage at P, and that's going to be our start piece. Vn equals Vp. So I just go do a P analysis. Well, if you come and look at it right here, P is connected straight to the ground. So the voltage of P equals 0. All right? Because the voltage of P equals 0, the voltage of N equals 0, and you end up with the simple statement, V out equals negative 40. And that is the answer. Okay? Now, before I turn off this video and put this one to rest, I want to talk about the special condition of what happens when you have constraints on this op amp. So there are three rules. First rule, you have no current going into and out of it. The second rule is the voltage of N is the voltage on P. And the third rule, all right, is we have these terminals and they represent the power of the op amp. That's VCC minus and VCC plus. Well, technically this is minus and this is plus because of the way it's drawn. All right, so here's my question. This would be my answer, but now let me put an addition. So I'm going to say put a little arrow here and I'll say if VCC existed between plus and minus, and let's say it was on 35 volts, then what would the answer be if this were the powering constraints of that op amp? Well, the op amp is supposed to spit out negative 40, all right? Given that it has this construction, it's supposed to, in an ideal sense, if it had no limits, it would spit out negative 40. But because it has a limit of plus or minus 35, negative 40 is outside of that bound. Thus, the maximum that this op amp can actually produce is negative 35. VO, with this constraint, has to actually be checked and be rewritten as 35 volts, all right? So we have this interesting situation that happens that students should always pay attention to. You always want to check what you get, all right? What you get with what the op amp can actually do, because this is technically theoretical unless the op amp can actually provide that sort of power. In this case, let's say we did not have the 35. If it were limitless, it would be 40, negative 40. In the case of it having a limit of negative 35, then the answer has to be fixed to negative 35. Okay, so hope that helps.